Download this code from codegive.com, link in the description below. Redefining geospatial data versioning, the geogit approach, a deep dive. Geospatial data is inherently complex. It changes constantly, requiring robust versioning to track edits, manage collaborations, and ensure data integrity. Traditional version control systems struggle with the large, binary nature of many geospatial formats. Enter geogit, a revolutionary project designed to bring the power of Git version control to geospatial data, offering a powerful and scalable solution for managing geospatial data sets. This comprehensive tutorial explores geogit, covering its core concepts, installation, usage, and code examples, demonstrating how it redefines geospatial data versioning. The problem: traditional versioning limitations with geospatial data. Before diving into geogit, let's understand the limitations of traditional version control systems, like Git for non-geospatial data, when applied to geospatial data. Large binary files. Geospatial formats like shapefiles, GOTIFFs, and GeoJSON can be very large, especially when dealing with high-resolution imagery or complex geometries. Storing these in Git repositories can lead to performance issues and large repository sizes. Lack of geospatial awareness. Standard Git is designed for text-based files and doesn't understand the spatial structure or semantics of geospatial data. It treats the entire file as a single unit, even if only a small portion of the data has changed. This makes diffing and merging difficult and inefficient. No attribute level tracking. Traditional Git tracks changes at the file level. You can't easily see which specific attributes of a feature have been modified between versions. This granular tracking is often crucial for geospatial data management. Limited branching strategies. Complex geospatial projects often require branching to explore different scenarios or test new data. Without geospatial awareness, merging branches with conflicting geospatial data can be a nightmare. 2. Introducing geogit, version control for geospatial data. GeoGit directly addresses the limitations of traditional version control by offering a geospatial-aware, distributed version control system built on top of the Git foundation. It understands the underlying structure of geospatial data and provides specialized commands for managing changes, diffing, and merging. Key features of GeoGit geospatial awareness. GeoGit parses and understands geospatial data formats, shapefile, GeoJSON, GeoPackage, PostGIS, etc. It tracks changes to individual features and attributes. Efficient storage. GeoGit can store large geospatial datasets efficiently by leveraging Git's object storage mechanisms, delta encoding, and potentially storing only the differences between versions. It also allows you to configure external storage for the actual geometry data. Granular versioning. GeoGit tracks changes at the feature and attribute levels, providing detailed information about what has been modified, added, or deleted between versions. Geospatial diff and merge. GeoGit provides geospatial-aware diffing and merging capabilities, allowing you to visualize and resolve conflicts based on spatial proximity and attribute values. Branching and collaboration. GeoGit allows for complex branching strategies, enabling parallel development and experimentation with geospatial data. Data provenance. GeoGit maintains a complete history of all changes, allowing you to track the provenance of your geospatial data and understand how it has evolved over time. Distributed architecture. Like Git, GeoGit is a distributed version control system, allowing for offline work and collaboration among geographically dispersed teams. Asterisk integration with existing tools. Asterisk geogit can be integrated with existing geospatial tools and workflows, such as QGIS, GeoServer, and other GIS software. 3. Installation and setup. GeoGit can be installed in a few ways, depending on your operating system and preferences. A. Installation via Conda, recommended for Python integration. This method is highly recommended as it allows for easy management of dependencies, especially when working with Python geospatial libraries like GeoPandas. 1. Install Anaconda/Miniconda*. If you don't already have it, download and install either Anaconda or Miniconda from https://www.anaconda.com/products/distribution, https://www.anaconda.com/products/distribution, or https://docs.conda.io/n/latest/miniconda.html, https://docs.conda.io/n/latest/miniconda.html. 2. Create a Conda environment, optional but recommended. 3. Install GeoGit via Conda Forge*. Conda Forge is a community-led collection of Conda recipes, and usually has the most up-to-date GeoGit package. 4. Verify installation*. This should print the GeoGit version number if the installation was successful. B. Installation from source, for advanced users or specific builds. This approach offers greater control but requires more technical expertise. You'll need to install the Java Development Kit, JDK, Maven, and Git first. 1. Install JDK, Java Development Kit. Download and install the latest JDK from https://www.oracle.com/java/technologies/javasdownloads.html, https://www.oracle.com/java/technologies/javaz-downloads.html, or use your system's package manager, example apt install default JDK on Ubuntu. Make sure the Java_home environment variable is set correctly. 2. Install Maven*. Download and install Maven from https://maven.apache.org/download.cgi, https://maven.apache.org/download.cgi. Add Maven's bin directory to your path environment variable. 3. Install Git*. Ensure you have Git installed on your system. 4. Clone the GeoGit repository*. 5. Build GeoGit*. 6. Configure the geogit command*. Find the geogit CLI/target/geogit executable in the geogit directory you cloned. You'll need to make this executable available on your system's path. A simple way to do this is to create a symbolic link in a directory that's already in your path, example /usr/local/bin. Replace /path/to/geogit with the actual path to the cloned GeoGit repository. 7. Verify installation*. This should print the GeoGit version number if the installation was successful. C. Installation via Docker. Docker provides a containerized environment, simplifying the installation process and ensuring consistency across different systems. 1. Install Docker*. Download and install Docker Desktop from https://www.docker.com/products/docker-desktop, https://www.docker.com/products/docker-desktop. To use a pre-built GeoGit Docker image*. Look for an official or community-maintained GeoGit Docker image on Docker Hub. For example, you might find one based on the GeoTools project, which GeoGit relies upon. A basic setup might look like this. Build the Docker image, docker build tgeogit. Run the Docker container, docker run it $. pwd/data geogit, this mounts your current directory as /data inside the container. 3. Verify installation *. Replace container_id with the actual container ID. 4. GeoGit workflow, essential commands and concepts. GeoGit's workflow closely mirrors Git's, with some geospatial specific additions. A. Initialization *. Geogit init initializes a new GeoGit repository in the current directory. This creates the .geogit directory, similar to .git. This creates the metadata store, using H2 database by default. B. Adding data *. Geogit adds shapefile GeoJSON geopackage, adds geospatial data to the GeoGit staging area, the index. GeoGit analyzes the data, parses the features, and stores them in its internal data structures. GeoGit reads the features and geometry from the shapefile and stores them internally. *geogit adds all files in the current directory. Be cautious with this command as it can add large unnecessary files. C. Committing changes *. Geogit commit mycommit message, commits the changes in the staging area to the GeoGit repository. This creates a new snapshot of the data. The M flag specifies a commit message, which is crucial for documenting your changes. D. Viewing the repository status *. Geogit status displays the status of the working directory and the staging area. It shows which files have been modified, added, or deleted, and whether they are staged for commit. E. Viewing the commit history *. Geogit log displays the commit history of the repository, showing the commit messages, authors, dates, and commit IDs. F. Diffing *. Geogit diff shows the differences between the working directory and the staging area, or between the staging area and the last commit. Geogit diff feature_ID shows the differences for a specific feature based on its ID. This is where GeoGit shines, as it shows attribute level differences. Geogit diff commit_ID1 commit_ID2 shows the differences between two commits. G. Branching *. Geogit branch_name creates a new branch. Geogit checkout branch_name switches to a different branch. Geogit merge branch_name merges a branch into the current branch. H. Exporting data *. Geogit export shapefile GeoJSON geopackage output_file exports the data from the GeoGit repository to a specified geospatial format. You can export specific branches or commits. Geogit export rev head states_exported.shop exports the latest commit on the current branch to states_exported.shop. Geogit export rev commit_id states_exported.shop exports a specific commit. V. Code example, a practical workflow with Python and GeoPandas. Let's create a practical example demonstrating a GeoGit workflow using Python and GeoPandas. This assumes you have Conda and GeoGit installed as described earlier, and a GeoPandas environment set up. Explanation *. One setup * we create a sample geodata frame using GeoPandas and save it as my_data.geojson. 2. Initialization * we initialize a GeoGit repository in the current directory using geogit init. 3. Add and commit * we add my_data.geojson to the staging area using geogit add and commit it with a message using geogit commit. 4. Modification * we modify the geodata frame by changing a value, altering a geometry and adding a row. 5. Add and commit, again we add the modified my_data.geojson and commit the changes. 6. View history * we use geogit log to view the commit history. 7. Diff * we use geogit diff head *head to see the changes between the last two commits. This will display the changed value, geometry, and the newly added feature. 8. Show diff for feature, demonstrates how to show change history for a particular feature using its OID. 9. Export * we export the latest version of my_data.geojson to my_data_exported.geojson using geogit export. 10. Geogit commands wrapped in Python, we wrap the geogit commands in a function run_geogit to easily execute them through Python. Important considerations for the code example *. Error handling * the code example includes basic error handling, but you should implement more robust error checking in a production environment. Dependencies * make sure you have GeoPandas installed in your Conda environment. Feature IDs, OIDs GeoGit automatically assigns unique IDs to features. These IDs, often called OIDs, are crucial for tracking changes to specific features using commands like geogit diff feature_ID. You will need to observe the logs and diffs to identify the IDs. Also be mindful of whether features are deleted and replaced vs actually modified, as that affects the OIDs. Geometry representation * the GeoJSON format stores geometry as text strings, well-known text, WKT. 6. Advanced GeoGit concepts. Remote repositories * like Git, GeoGit supports remote repositories, allowing you to collaborate with others on geospatial data. You can use standard Git hosting services, example GitHub, GitLab, Bitbucket, to store your GeoGit repositories. Conflict resolution * when merging branches, conflicts can arise, especially if the same features have been modified in different branches. GeoGit provides tools to help you resolve these conflicts by comparing the conflicting versions and choosing the correct data. Hooks GeoGit supports hooks, which are scripts that are automatically executed at certain points in the GeoGit workflow, example before a commit, after a push. You can use hooks to enforce data quality checks, automate tasks, or trigger notifications. Configuration GeoGit offers a wide range of configuration options to customize its behavior. You can configure the storage format, the diff algorithm, and other settings. Database backend GeoGit supports different database backends for storing its internal data structures. The default is H2, an embedded Java database, but you can also use PostGIS or other databases. Using PostGIS offers significant performance benefits for large datasets and complex geospatial queries. 7. GeoGit alternatives. While GeoGit is powerful, consider these alternatives depending on your specific needs. PostGIS with versioning * if you are already using PostGIS as your primary database, you can implement versioning using database triggers, audit tables, and stored procedures. This approach provides fine-grained control over versioning but requires significant database expertise. File-based versioning with Git LFS Git large file storage, LFS, can be used to manage large geospatial files in Git repositories. However, Git LFS doesn't provide geospatial awareness or attribute-level tracking. Delta encoding and compression * techniques like delta encoding and compression can be used to reduce the storage footprint of geospatial data in traditional version control systems. However, these techniques don't address the lack of geospatial awareness. Proprietary geospatial version control systems * some commercial GI software packages offer built-in version control capabilities. These systems can be expensive and may not be as flexible or scalable as GeoGit. Geo package this open standard database container for geospatial data can include versioning elements. Geoserver and version data Geoserver can be configured to serve versioned geospatial data from sources like PostGIS or GeoGit. 8. Conclusion. GeoGit provides a revolutionary approach to geospatial data versioning, addressing the limitations of traditional version control systems. By understanding the core concepts, mastering the essential commands, and leveraging Python and GeoPandas for practical workflows, you can unlock the power of GeoGit and manage your geospatial data with greater efficiency, collaboration, and integrity. While the project has had periods of inactivity, it still remains a valuable concept and tool, and its influence can be seen in other geospatial versioning approaches. Remember to explore the official GeoGit documentation and community resources for more in-depth information and support, as the project may have continued its development since this tutorial's creation. Consider the alternatives if GeoGit doesn't fully meet your needs, and continuously evaluate the best approach for managing your valuable geospatial data.